you add 1 to the exponent, divide by the new exponent. So it becomes minus 9x squared over 2. And that doesn't reduce either. And then this last one, it's kind of one of those special ones where you have to have another rule here. If you take the integral of a constant, it always becomes that constant times x. So this last one becomes just 4x. So in terms of your answer here, you just combine all of these 2x squared plus 10 over 3x cubed minus 9 over 2x squared plus 4x. And then last little thing here, you have to use a capital C here. All these problems have what's called a constant of integration, which we can talk about at a later time if we need to, but you can just for now assume it's all there. And I'm sorry, I got an exponent wrong here. This is 2x to the 4th, not 2x squared.
Okay.
So let me know when you get this down.
Okay.
Are you possibly sick? Unwell?
Potentially.
Okay.
I also haven't been talking today, but yes, I am going through something.
Okay. We'll limit how much interaction you have today. Keep the voice going. So what's maybe possibly interesting here for you is, as you know, sort of has some understanding of like derivatives. The derivative of this is exactly what we started with. And so there's this relationship. Yeah. So you go derivative is this way, integral, this symbol goes the other way. Basically going backwards in the course.
So
Okay.
that plus C at the end.
Yes. Must be there.
Okay.
Capital C.
Is it because of that dx?
Yes, it's because the derivative of a constant is always 0. So it's going to go away. Like, let's just say it's 5. We don't know what it is. We'll maybe have some problems where you have to find it, but for now, you just have to put it in every time.
Okay, I think I got it all.
Okay. All right, let me go to the next one here. All right, it says evaluate the following integral. So same thing. This time though, you need to perform a little algebra first. You want to distribute in this 3x squared to both. So you get 3x to the 5th. When the bases are the same, you add the exponents plus 18x squared dx. And then it's just like the last problem where you take the exponent and you add 1 to it. So it becomes 6 and you divide by the new exponent 6 and then bring this 3 down. X squared becomes x cubed divided by 3. And then you bring the 18 down. So that's 1/2 x to the 6th plus 6x cubed plus c when you reduce. So if you were to take the derivative of this, you would actually get back to the original. So you might think, okay, I've got it, you know, lesson's over. They do get more difficult.
Oh, I'm sure.
The first thing they do is they introduce fractional exponents, which really isn't any more difficult. It's the same process. You have to add 1 to the fraction. So like 5/2 plus 1 is really 5/2 plus 2/2, which is 7/2. So it becomes x to the 7/2 over 7/2. Bring the 6 down, minus, and then it's x. Now this time, 7/6 plus 1 is 7/6 plus 6/6, which is 13/6. You divide by the new exponent, 13 there. Now, you don't leave it like this. As a reminder here, when you divide by a fraction, it's the same as multiplying by the reciprocal. So it's 6 times 2/7, x to the 7/2, minus 13 times 6/13, x to the 13/6, plus c. And so sometimes you get some nice reductions here. So it's 12 over 7 x to the 7 halves minus 6x to the 13 over 6 plus c, like that. But I think your Pearson would have accepted this top row. This is just a simplify step if you need it. Let me know when I can go on to the next problem here.
Okay, good.
Got it. Okay. All right. So it's kind of like when we first learned derivatives. There's these rules that you like exponent rules you have to remember here. So like this one is really the integral of 7x to the minus 2 power. And the rule is when you bring that x squared up, you make it negative. And so now you apply that same rule we just talked about, where you add 1 to the exponent, divide by the new exponent, and you bring that constant down. So minus 2 plus 1 is -1 over -1 plus c. So what you can do is the 7 and the -1 can go together. And if you recall, x to the -1 is 1 over x. So you can go over x here plus c as your final answer. A lot of stuff from previous courses synthesizing here, but you could also, again, I mean, you could actually enter it in one of these other lines and be correct. Did you get this down? Can I move on to the next one?
Yes.
Okay, great. All right, so the next one is a kind of a new problem here. Notice there's an e. It's no longer like x to the 5 or x to the -1/2. It's e. So you need a new integral rule. Well, the integral of e to the x is e to the x. It's the only one that is itself. Okay, and you remember the derivative of e to the x is itself. But problem is it's not just x. There's this minus 0.5 x here. So this moves us to the first, well, I guess I won't quite do it. So the answer is, and I'll address this later on, is itself. It's got to be itself. But when you take the derivative of this, you have to, you're going to get a minus 0.5 out in front. Like if you came over here to the right and you're like, all right, what's d dx of e to the minus 0.5x? It's e to the minus 0.5x times negative 0.5. So to undo that, you have to divide by it right here on the bottom, because then they cancel out. So the idea is, like, if you put a minus 0.5 here, you get a minus 0.5 here, and then they cancel. And that's how you get back to the original. You bring this 5 down like that, and then you add c. So again, like, just if you're allowed to grab a calculator if you need to, but 5 over minus 0.5, it's over -1/2. So it's really minus 10 e to the minus 0.5x plus c.
Okay, got it.
All right. So I thought we were moving into what are called u-substitutions, but not quite yet. So that's why I just sort of made that. It didn't go into it, just sort of like we figured it out without giving it a lot of emphasis on the u-substitution. So this one looks really awful, okay, but it's still in the same category of like problems we've been doing. You just need to rewrite this with the exponent. So it's x to the 1/2 plus 3 over 4 times x to the 1/3. So there's an exponent root property where the 3 becomes the bottom number and the exponent becomes the top number over here. That dx. Okay, now this 4 is really, I'm gonna rewrite it, it's really 1/4, and constants can always come out, and that's another property here that's useful. But where we're going with this is there's only one term on the bottom, so you can actually divide each of these by that. It's x to the 1/2 over x to the 1/3 plus 3 over x to the 1/3. And we're just simplifying the exponents here. So when the bases are the same, you subtract the exponents. So you got to do 1/2 minus 1/3, which ends up being 1/6. So you have x to the 1/6. We're just simplifying inside here. And then on the right here, that exponent becomes negative. So now we can get to something we can apply the power rule. So the whole point of this problem is to be able to simplify to something that you can go back to using the power rule for. So to do this again, you add 1 to the exponent, so it's 7/6. You divide by the new exponent, and this 1/4 comes down, plus, again, you add 1 to the exponent, so it becomes 2/3 over 2/3, like this, plus c. All right, so now we're just going to do a little simplifying here. So the 1/4 applies to both, so it's really 1/4 times, and then you flip the bottom, 6/7, x to the 7/6, plus 3/4, because 3 times 1/4 is the 3/4, times the flip, 3/2, x to the 2/3 plus c. And then just simplifying here a little bit, that's 3 and 2. So we got 3/14 x to the 7/6 plus 9/8 x to the 2/3 plus c. And that's your final answer for this one. Just check that these are all reasonable here. Looks okay.
Okay, I think I got it. Yep.
Okay. All right, so it looks like we're moving into some word problems here. But it's the same concept. We're going to be taking what's called the antiderivative or the integral of all these. So, all right, so it says here, find the cost function if the marginal cost function is c prime of x equals 6x plus 3. So what they're asking you to do is to integrate 6x minus 3 dx. Okay, and this is not that hard. You've got the power rule we've been doing. So you add 1 to the exponent, divide by the new exponent. And then on the constant one here, you put an x plus c. So this is your cost function, okay? But this time they give you information to be able to find c. So before we do that though, let's just reduce 3x squared minus 3x plus c. So the fixed cost means that the cost of 0 units is 9. So x is 0 and c of x is 9. So you plug those in, you say, okay, 9 equals 3 times 0 squared minus 3 times 0 plus c. So you're putting the 0 in for x, c of x is 9, and you solve for c. So these go away. You end up getting 9 equals c, and that goes back into this line right here. So, or actually the next line would be better right here. So your cost function is 3x squared minus 3x plus 9. So the idea again is you take the antiderivative, which we did, we've always been having this C and we haven't really talked about it, but you can find C sometimes if they give you information. So we found the value of C and we plugged it back in to write our cost function.
Got it.
Got it. Okay. All right. Now the value of C is not always the number they give you. Sometimes it is, but it just, you don't want to generalize with that. You want to, excuse me, you want to really be sure that it is that by solving it. Okay, so another kind of application story problem here. So they say here is the derivative. They give you the derivative. So you want to take the antiderivative. You want to integrate this 0.01071 t plus 2.09. So you can use any variable just like we did with derivatives. Like it could be a t, could be an x, and so on. So when we find the antiderivative of this, it's again just using the power rule. Even though these are decimals, it becomes 0.01071 t squared over 2 plus 2.09 t plus c. Okay, and that's your P of t function. But we can find C now because they tell you in 2012 the number of patents, it was 32,799. So they're telling you when t equals 12, P of 12 is 32,799. All right. So this is where we have to do a little more work. They're giving you the left side. They're telling you it's 32,799 equals 0.01071, 12 squared over 2, plus 2.09 times 12, plus c. So we need to solve this for c. So to do that, you evaluate the stuff on the right and then subtract it over. It does say an exact answer, so I guess it works out nicely. So let me get that here. 32,799 minus 0.1071. Okay, so the value of C is 32,773.14888. Tens and thousands. Just wondering if there's one of these weird, like we're supposed to multiply by 1,000 somewhere. T represented, P represented time pence and thousands. Yeah, so I think actually it's I should have put 32.799 in here because they're saying that P represents the number of design patents in thousands. So this number right here is not in thousands, so we've got to convert that to 0.799. So just that'll change our answer slightly. Yeah, it makes more sense. Okay, so this is completely wrong. Let me get this out of here. 6.94788. So your first box there, your first P of t is, we got to take this 0.01071 divided by 2. So that is 0.005355 t squared plus 2.09 t plus 6.94788. So that's what goes in that first box there. Now to find the answer to part B, you take this equation for part B and it wants it in 2024. So that's t equals 24. So we evaluate when t is 24, this equation, but again, you have to deal with this like fact that it's in thousands. So you have to multiply your answer by 1,000. Okay, so I got my answer, but I'm going to multiply by 1,000. They really threw in a really challenging problem here. So it says to round to the nearest whole numbers needed, 60,192 patents, no comma on that. That's the rounded number for part B. I hope there's no questions because a long question. Oh boy. Okay. We'll move on to next question here. Another application problem. Does your company do a lot of patents? Curious. Do you know?
No, we don't, but management is encouraging the engineers to do more.
Yeah, that way yeah, it's not a good deal for the engineers, frankly.
No.
They almost never get any royalties out of that. But I guess that's why they're being paid.
Yeah, true.
Yeah. All right, so this is kind of the same problem here. They give you some sort of function and you got to find the antiderivative of that. We kind of looked at one earlier where I said, well, the antiderivative of E is itself, okay? It's but then you have to divide by the part in front of the variable. And then you have to bring down the constant here. So you actually get a cancellation here. So f of t ends up being minus e minus 0.03 t plus c. And they don't give you the initial condition. Okay. Maybe they're trying to tell you that the rate of like it's initially 0. It's odd because there's no way to find the constants. Let me just check this problem on the web here. We'll see if someone else has some ideas on how to do this. So it doesn't say this. This is the problem. This is what's not clear. So part B gives you the initial condition, but I'm not sure what to tell you to put in part A. I think we should find we should find the value of C and use that for part A. So the idea is that if there's 0 units there, it's the same as saying putting 0 in for T. And you might think that C is 0, but e to the 0 is actually 1. So this becomes 0 equals -1 plus C, and then you add 1 to both sides. So C ends up equaling 1. So your f of t, what I would put if this were me would be 1 minus e to the minus 0.03 t. I would probably do that for part A. For part B, you're just evaluating at 12. And that's not too bad. So you just put 12 in for t, e to the minus 0.03 times 12. Grab a calculator, just say to round to 3 decimal places. Okay, 0.302 for part B. Let me know when I can go on to question 10.
I'm ready.
Okay. So question 10 comes from physics. It's the we've kind of looked at this already in terms of like position, velocity, acceleration, but now we're going backwards. So they give you an acceleration function, or they give you the acceleration. So v of t is the integral or the antiderivative of a of t dt. So your v of t is the integral of minus 30 dt, which is minus 30t plus c. Okay, so like imagine if you take the derivative of minus 30t, you get minus 30 up here at the top. Now they tell you the initial velocity is 0. They say v of 0 equals 0. So that's enough to be able to find the constant of integration. You plug 0 in for t and 0 in for v of t, and you get c is 0. So that goes back in here. It doesn't really help us much, but v of t is minus 30t. Position is the antiderivative or the integral of v of t. So you just plug in your equation there. You got your v of t is minus 30t dt. Use those integral rules we've been talking about where you add 1 to the exponent and divide by the new exponent plus c. So your s of t is minus 15t squared plus c. And if you go back to the original part of the problem, it says an object is dropped from a small plane flying at 5,415 feet. So they're saying at time 0, the height is 5,415. That's your s of t. And you're putting 0 in for t, and you're getting c. So c is 5,415, and you plug that back in. So there's your first box. S of t is minus 15t squared plus 5,415 using those initial conditions. The next part of the question, so I'm sorry, so picture here what's happening. You drop, plane's flying, it drops out, and it hits the ground. Something like that. And so now part B is figuring out the time where this happens. So to do that, you're just setting this equal to 0, and you're solving for t. So this isn't even a calculus question anymore. It's just a can you get the variable by itself question. So it's minus 15t squared equals minus 5,415. Divide by minus 15. And then you can take a square root of that. And it does say to simplify your answer. That's interesting. Maybe it works out nicely. And it does. It's 19 seconds. Again, I've never jumped out of a plane. I've never wanted to. I don't know if that's reasonable or not. 19 seconds to hit the ground. Yeah.
All right, got it.
I got it. Okay. All right, now we're back to, now this is moving into a new territory on the integral front. So we're done with the application problems, and we're like, hey, let's get back to integrating these things. Notice there's a power of 5 out there. That's why you can't just distribute in. So we're doing what are called u-substitutions, and you saw those when we did derivatives. We would like let u equal the numerator or denominator or the product, using the product rule. And the hardest thing about this is actually picking the u, but you've got me to pick, so you're going to be able to help. It's going to help here a lot. Students really struggle here with like what to make the u. And I give them a list of rules. I'll say, well, it's usually what's in parentheses, exponents, under a root, denominators, things like that. They're just guidelines though. There's variations in every problem.
Okay.
So that is your first box here. Now we will actually have to integrate using the u's, but not in this first problem. So du means to just take the derivative of this. And this is another kind of place where most students really struggle in this course, because they're like, oh yeah, I got to integrate, I got to take derivatives. And they mix up the rules because they're learning them for the first time. So the derivative of 3x to the 4th, bring the 4 down, times 3. 4 times 3 is 12. Subtract 1 from the exponent. So this is your second box there for your answer. And in the next problem, I'm assuming we're actually going to use these to integrate. All right. So while you can take a derivative of everything, you cannot integrate everything. They're much harder. And that's really the like calculus 2 in a traditional calculus progression. Like you spend a lot of time in the second semester course doing these types of problems. And these are not the hard ones. These are just the introductory ones. But the point is like you can go one direction is very easy, but going backwards is very hard. So it says u-substitutions. They're telling you like, hey, you need to make a u-substitution, and it will help here that I'm giving you the substitution. So du is 16x plus 12 dx, and then what I tell students here is to solve for dx. So dx is du divided by 16x plus 12. Just moving it to the other side of the equation. Now you might think, well, what does all this mean? We're gonna substitute it in on this thing on the left here. So we don't have a substitution for 4x plus 3, so we keep that. We do have one for this thing inside parentheses, it's u, and dx is really du over 16x plus 12. Now the idea is that all the x's go away. And you might say, well, they haven't all gone away, and I'd say you're right. But what we can do here on this 16x plus 12 is factor out of 4, and that gives you 4x plus 3. And now the 4x plus 3 cancels, and the 4x plus 3 cancels. So the x's are now gone. And it becomes the integral of 1/4 du over u to the 4th. So we'll do just a little bit here to make this easier to work with. We'll move that outside. 1 over u to the 4th is u to the minus 4. So it's 1/4 integral u to the minus 4 du. And now we can use those power rules that we talked about in the beginning of the lesson here. So you add 1 to the exponent, divide by the new exponent, plus c. So it becomes negative 1 over 12, 1 over u cubed, because that u to the minus 3 becomes 1 over u cubed, plus c. And then the last step is to back substitute your u. 8x squared plus 12x. So it's minus 1 over 12, 1 over 8x squared plus 12x plus c. To the power of 3. There it is. So I don't know if you got all that, and it's okay if you didn't, but we're going to repeat here. Looks like for a couple of problems. The next few problems are kind of the same in terms of this structure. All right, so let me grab the next one here. So I guess let me point out one thing. The original problem we got it down to this, which is much more doable. And that's the game in all of these. Like we're going to make the original problem, which looks really complicated, into something that's very doable. All right, so it says u-substitution again. They're referring to a u-substitution, and I'm going to give that to you. I'm going to tell you it's the exponent 9x to the 9th. So your du, got to take a derivative here, is 81 x to the 8th dx. And then I recommend solving for dx. dx is du over 81x to the 8th. And so you substitute back in for the things you have. Like you have the exponent 9x to the 9th, that's u. And dx is du over 81x to the 8th. And what you really hope for is you get a cancellation. And you do. X to the 8th cancels with x to the 8th. 9 over 81 is really 1/9. That's nice. So I'm going to bring that outside. So it's 1/9 integral e to the u du. So these u substitutions really make the integral a lot simpler. Integral of e to the u du is itself e to the u. So we don't have to do any manipulation here. It's e to the u plus c. And then you have to do that back substitution again. You say, oh yeah, u is really 9x to the 9th. So this is 1/9 e to the 9x to the 9th plus c. There's your final answer on that. So if you took a derivative of this, you would get back to the original. Again, that's always the case. Okay, so let's move on to the next one here. All right. Here we go. Use substitution to find the definite interval. So same thing again. It's like, well, what is the use substitution? So one of the other things I tell students oftentimes is whatever your u is, its derivative needs to be in the back in the integral. So you'll see that here. You get 4t cubed dt, and that t cubed is there, and so that's a good sign. That's like, all right, I think we're on the right track here. Students really struggle to guess what the u is because there's only really one choice that works, and if you don't choose it wisely, you just go down the wrong path over and over again. So you substitute in for what you know, which is your u. You always want to see a u in there, and then you always substitute in for that dt or d x or whatever. And what you hope for is that your original variable, which in this case is t, that it cancels. So a lot of 1/4, a lot of 1/4 here. So it's integral 1/u du. So this is a new one for us. Integral 1/x dx becomes the natural log of the absolute value of x plus c. Those absolute values are very important, especially when you enter them in your answer space there. So this becomes 1/4 natural log absolute value of u plus c. And then you want to grab your u from earlier, and you back substitute that back in. It's just like with the derivatives, we would use u's and v's, du, dv, v prime, u prime. You have to put that back in to the original here. So again, just make sure you've got those absolute values in there.
Got that one.
Okay. So the next one here, kind of the same thing again. It's it doesn't tell you to use a substitution, but that is the only way to figure these out. So it says determine the indefinite integral. And again, you got to figure out, well, what's my u? Your u here is natural log 9x. And you might say, well, that's not the entire denominator. But again, your derivative has to be in there. So your derivative of this natural log 9/x, you'll see will be in there. So again, they're just guidelines. There's no perfect, like this always works. So the derivative of ln is 1/, whatever's inside. So it's 1/9x. But with the chain rule, got to remember your derivatives. Take the derivative of 9x times 9. So this just becomes 1/x dx. And again, I recommend solving for dx. Dx is x times du. So now you plug in for what you have, always your u, and then always for your dx, which is x times du. And when you know it, the x's cancel. So it really works out nicely. 17 comes out, 1/u du. And this is another one of those natural log from the last problem. Natural log absolute value of u plus c. Bring the 17 down, and your u is natural log of 9x. So a little awkward here because you're using absolute value, but the inner one is not absolute value. So it may just be harder to enter than it actually is to see the answer, but make sure you got those absolute values on the outside. You can use parentheses on the inside, or I don't even know if you need them on the inside. I don't know. Remember, Pearson will take that. Got it? Okay. And if at the end you want us to go through all of them again just to confirm, that's fine with me. So again, evaluate the integral. You are going to make a substitution here. This time it is the entire denominator, So, and you'll see here that its derivative 4 is 0, but the derivative of e is itself, but then you multiply by the derivative of the exponent, which is 3. And you're like, oh yeah, that's in there. That's in the numerator. Like you feel good about like that. You're like, okay, I think that'll probably work out. And again, you substitute back in the integral for what you have, meaning the u and the d and the dt. So you always have some t's there to start, and then you're really hoping that everything cancels out. 3t, and it does. This cancels out perfectly. Okay, so sometimes they just work out really nice. 1 over u du. And this is the natural log of the absolute value of u plus c. And your u is that denominator. So let me know if you want us to go back and look at any of the previous problems to just confirm that you've got them down correctly.
Yeah, that probably wouldn't hurt. We can probably start at we'll just start at 1.
Okay. Sure. 1 here. Just looking at myself, that does look okay to me. 2x to the 4th. I think I made an error the first time I went through this.
Okay.
The second one, 3x to the 5th plus 18x squared. Okay, looks good.
Okay. Okay.
Good. Did you get this one?
I did.
Okay. I think the rest actually were probably, well, I'd take that back. There's a couple more that got.
That was good.
That one's good. This one. 1/2 of that is 5e. Looks okay. This one down here, this would be hard for me to check. Just make sure that's 2/3 there, if you can see that.
Okay.
All right, now we're moving into the ones that 3x squared, so 6x minus 3 plus 9. Yeah, that's right.
Okay.
This one would also be hard to check, but I think we've got it. The answer was reasonable.
Okay.
Let's keep going here. Oh yeah, there it is. 1 minus e to the 0.03t. Yeah, that's derivative is that. Okay, 0.302. And then this one here, minus 15t squared. Yeah, that works for that. We have 0, 0, 5, 4, 1, 5. Okay. And then that was really nice. So just 19. I circled the
Gotcha.
yes, got that. All right, then we moved into u-substitutions. Oh yeah, this is the u, 12x cubed. Yep.
Okay.
That's last. Sometimes these are hard to enter, but I mean, just make sure you got the right formatting. I mean, you could clean this up a little bit, but does work.
Okay.
Plus C's in there. That's really important. Yeah, 1/9 x to the 9th. Yeah, there's 9x to the 9th. Cancels out. Okay. All right. So 1/2 to the 4th, 14 cubed. Cancel that. Yeah, this looks good. 17 times 1/that times derivative of that. Yeah, works.
That's good. That's 4 plus e to 3t.
Yes. Yes.